a little more terminology. The range of a linear transformation is a subspace of W. So that is a theorem, and we're going to skip the proof for now. It's in the book if you'd like to read it. The range would be a subspace of the codomain W. So W is the space that the range is embedded in. We saw an example previously where the range of W was all of R3, but the codomain was all of R3, but the range was just the XY plane, right? So when we sent this R3 into XY0, right? The W, the vector space that the range was embedded in is in R3, but the actual dimension of the range was 2, right? Because it spanned a plane. So let's see. So the range can be smaller than W, and now we have this saying that it's a subspace of W. The kernel we saw in the previous video is a subspace of the domain V. And the kernel is all the vectors that get sent to the 0 vector. So the range is the set of all the vectors that come out of your transformation. For example, here, if we have this transformation given by, so let's see, if we have a transformation that takes vectors and multiplies them by this matrix A on the left, then the vectors that you plug in have to be of dimension 5. So that means your transformation takes values from R5 and it puts vectors into R4, right? So the solutions will be 4-dimensional. So we saw earlier that the computation that I ended the last video with seemed like, so we were finding the solution space of AX equals 0. So we found that the solution space, or it was the same of AX equals 0, is the same as the kernel of the transformation T given by left multiplication by this matrix. So we saw that a basis for the kernel of T was made of these two vectors, right? It was -2, 1, 1, 0, and it was 1, 2, 0, -4, 1, 2 zeros here. There we go. So I have to make sure that the vectors in the kernel are 5-dimensional, right? Because they live in the domain V. So a basis for the kernel of T is made of these two vectors. That means the dimension of the kernel of T is equal to 2. This was also called the nullity of matrix A, if you remember from chapter 4. It was computed in exactly the same way. So let's see, the nullity of T would be 2 because in this context, the nullity is the dimension of the kernel. Before we said the nullity is the dimension of the solution space of this homogeneous system of equations. The rank now, we call the rank the dimension of the column space or the row space. Most particularly right now, we're going to say that the column space of A is equal to the range of T. So now we can reflect back on that and we can say, well, how did we compute the dimension of the column space of this? Well, we said it's the number of leading ones, right? So looking at the row-reduced matrix, the dimension of the column space of A is equal to 3, and that corresponds with the dimension of the range of T. So matrices don't have ranges, they have column spaces. Transformations are functions, so they have ranges. Both of these are named the rank of T or the rank of A. I wrote rank of A here out of sight, and I wrote rank of T there, and I didn't notice that I was out of sight. Right, so this is the rank of T, or it's also called the rank of the matrix A. Excellent. So let's see, what did we leave out? Yes, so we have a basis for the kernel of T. If I were to find a basis for the range of T, then I would need vectors in the column space. So I could take the corresponding vectors with the leading ones. And this would be the fourth matrix there. So that means a basis for the range of T could be made of 1, 2, -1, 0. That's this guy, because it corresponds to that leading one. And then I'm going to take this guy, because 2, 1, 0, 0 corresponds to the second leading one. And then the last one, 1, 1, 0, 2. And we notice that the vectors in the range of T have the same dimension as the dimension of the codomain. So they have to have 4 entries, right?